Stay up late though it rains. It's good, but it is never the same. Never really the same.
Alrighty, so let's do an application of what would we even use inverses for. So let's start with one function. We'll call it c of t is equal to 5 over 9 times t minus 32. Okay, so some of you might recognize this as the equation which gives you the conversion between degrees Fahrenheit and degrees Celsius. Okay, and this actually converts, so t represents degrees Fahrenheit. Okay, so this converts Fahrenheit degrees, what at some temperature, into degrees Celsius. Okay, so what's really going on here, I guess more pictorially we could say, is that degrees Fahrenheit is being plugged in, so that's our input, right? And then the whole function, whatever this gives us out degrees Celsius. Okay, so the inverse function of this, we can notate it like this, because it doesn't have to exactly have that c to the negative 1 kind of thing, but it could be. I mean, we could just say f of t is equal to c inverse of t, okay? And this is going to be equal to 9 over 5 t plus 32, and no parentheses here, okay? So in this case, then we would be plugging in whatever t is here. This one now represents degrees Celsius, okay? So now we're going to go from Celsius to Fahrenheit. So when we plug in degrees Celsius into like kind of both of these, then what we get out is an answer in degrees Fahrenheit. So see how it works back and forth, right? So this way, because we don't only have this function, this top one here, which only went one direction, right, from degrees Fahrenheit to degrees Celsius, now with our inverse function, we can go backwards, or we can go in the opposite direction, right? So now we can go from degrees Celsius back to degrees Fahrenheit, which is pretty useful, right? So building off of that example, let's say we have c of 75 is equal to about, let's say, 24. Okay, and you would get that by plugging it into the top function on the previous slide. Okay, and what this represents is that, well, 75 degrees Fahrenheit is about equal to 24 degrees Celsius. Okay, and so you could see how using the inverse, f of 24 is equal to 75. You can see pretty simply how that works, because then this one just means, well, 24 degrees Celsius is about equal to 75 degrees Fahrenheit. Okay, so see how we made that conversion there. Again, this one was from Fahrenheit to, I don't know, I'm drawing two lines there, to degrees Celsius, and this one was from degrees Celsius back to Fahrenheit. Okay? So now the question is, well, how do we find this inverse formula? Does it just come out of thin air and we're supposed to know how to do it? The answer is no. What you do is you start with your original function, right? So in our case, this was our c of t is equal to 5 over 9 times, in parentheses, t minus 32, okay? So what we're going to do, and let's go back to concepts and everything. You know how from our original function, what our inverse function does is it takes the outputs from our original function and converts them back, or kind of processes the outputs and turns them back into the inputs, okay? So in essence, what we're going to do is change the variables, kind of. We're just going to swap our variables. So swap inputs and outputs, we'll say. Inputs and outputs, okay? And the way that we do that is that, well, what we can do is just say, well, c, we can just get rid of the t. That's just a notation thing. So c is equal to 5 over 9 times, and instead of t, I'm going to write an f here, okay? And at any time, just a side note, at any time, you're welcome to switch your variables or like change them just so they make more sense to you, so we don't have like random t's floating around here. But the thing is, when you change your variables, you have to remember what each one signifies, okay? So in this case, I change it to something that's understandable to me. This just means degrees Celsius, right? And this just means degrees Fahrenheit. So it's pretty self-explanatory there, because we're plugging in a temperature in Fahrenheit and converting it to Celsius, okay? So anyways, from that, once we write our equation, this is our original one, right? What we're going to do, in order to find your inverse, you just solve for the dependent variable, okay? So dependent meaning what you're plugging in, your input. So in this case, we're plugging in f, so what we want to do is just solve for f and get it by itself on its own side of the equal sign. Okay, so the first step to doing that is by multiplying by 9 over 5 on both sides to cancel out that fraction here, right? So 9 over 5. Okay, so these ones cancel out, and we get f minus 32 is now equal to, on the left side, we have 9 over 5 times c. Okay, and the last thing we have to do is add that 32, add the 32, and we get f is equal to 9 over 5 c plus 32. And that's it. That's pretty much all we had to do in order to get our inverse function. So f now is equal to inverse of c, or c inverse. Okay? And that would be it. If you wanted to write it in more formal terms, you could just stick back the t's if you want. So f of t, we're going to plug in whatever. That means our input would be equal to 9 over 5, and we can change the c back to temperature. Okay? But something, like I said, to keep in mind, that's why I took out the t's originally when I was trying to find the inverse, is that because we have t's in both of these equations, that could be kind of misleading, because it feels like we're plugging in the same t, but it's really not. Okay? So anyways, that's why I removed it in the beginning, but this is a formal definition of what your inverse would look like. Okay, something important to note about functions is that the following. So for a function, I'll just abbreviate, this means function, to have an inverse, because not all do. So to have an inverse, a function must pass a certain test or a certain requirement. So it must be 1 to 1. 1 to 1. And I'll just say a 1-to-1 function. We already know it's a function, but now we need to specify that it's 1-to-1, which means that for every b, well, function in the beginning, just to start off, function, remember, we'll just do a refresher. Function means that for every one input, you only have one output, right? And then 1-to-1 additionally means that for every output, you can only trace it back to one singular or unique input, okay? And the reason being why this is a requirement in order for a function to have an inverse is that when we reverse, or when we swap the variables, so when we swap the variables, or our inputs and outputs, right? The inputs become outputs and the outputs become inputs, etc., right? So when we swap the variables, every input into our inverse function now has to have only one output. Now has to have only one singular output. One output, A, that would be in this case. Output A. Like A. Okay? So, yeah, that's basically it. That's just something to look out for especially when we're graphing functions and trying to find inverse functions of graphs that we can see. Okay? Okay, so let's do an example where we utilize a graph and then try to find the inverse and graph that as well. Okay? So, we see this graph here. Okay, it's like a curve. It looks sort of like a square root, right? So anyways, what we're going to do from here, the first thing we have to check in order to even draw an inverse is that we have to verify that this function, let's call it f of x, right? This graph is the f of x one, that f of x even has an inverse, okay? And remember, like we said on the previous slide, and the only requirement for a function to have an inverse is for that function to be 1-to-1. Okay, so first of all, we just check, okay, so this is a function because it passes the vertical line test. Remember that? Okay, so it passes the vertical line test. That's good. And now how about the horizontal line test? That's to check if it's 1-to-1, and it looks like it is going to be 1-to-1. For each output, there's only one unique input. Okay, so we check that it's 1-to-1. We'll just check that off our list. 1-to-1 function. Okay, we're good to go. So that means our f does have an f inverse. So that's good. And now the only thing we have to do is just take, so what we're going to do is swap our x and y points. So actually, let me write it out. So we're going to take, these are the steps we're going to do. Take x, y points, okay, and graph the points y, comma, x, okay? So this basically just means we're swapping the inputs and outputs in order to get our inverse graph. So, for example, let's take this point here, right? That's 1, 0, and now we'll switch it, so now we get 0, 1, and that point is right here, okay? So there's 0, 1. Let's take another point. So we have, how about 2, 1 on our original graph, and now we'll have 1, 2. So it's up here. Alrighty, let's see, what else do we have? 4, comma 2 is on our f of x graph. So now we'll have 2, comma 4. So all the way up there. Alrighty, and now let's do something on the left. So now let's say, well, on our original graph, as x approaches 0, then we have our graph going down to negative infinity. Okay, so if we have the point kind of like this, which isn't really a point, but anyways, so we have some kind of trend, right? As x goes to 0, our f of x goes to negative infinity. So if it goes the other way around, if our x goes to negative infinity, then the value of our function, of our inverse f, should be going to 0. So that means as x goes this way, the function is approaching 0, okay? Closer and closer to 0. Alright, so let's connect the dots, and we get something that looks like this, like a curve, right? So this one that I just drew is our inverse of f. And something important to note, it's kind of cool, I think, but what we did, essentially, by taking our original points, our xy points, and swapping the coordinates, right? Swapping our inputs and outputs in order to get the graph of our inverse, what we did in order to do that is basically reflect things. What we end up with is a reflection of our graph across the y equals x line, okay? Across the line, across y equals x line. Isn't that neat? It's pretty symmetric, right? You could flip it, you could like fold the paper or fold the screen on that dashed line that I just drew, and our graphs would match up. So anyways, that's kind of an interesting phenomena that occurs with functions and their inverses. Okay? Alrighty, well that wraps up the section on inverse functions. I hope that helps, and I'll talk to you in the practice problems video if you watch.